Welcome! Today, we'll be tackling LeetCode problem number 1199, minimum time to build blocks. This problem challenges us to optimize the time required to assemble blocks by dividing tasks strategically among workers. Let's dive in and explore the solution step by step. The problem requires us to determine the minimum time needed to build a set of blocks using workers. Each block has a specific build time given in the blocks array, and we start with only one worker. However, we can split a worker into two workers to parallelize the work, though splitting comes with a time cost specified by the split parameter. Each worker has two choices: they can either build a block, which takes the time specified for that block, or they can split into two workers, adding the split time. The key challenge is to decide how to optimize the use of workers, whether to split them or assign them to blocks, to minimize the total time required to build all the blocks. To solve this problem, we need to return a single integer representing the minimum time required to build all the blocks. Let's look at some examples to understand this better. In the first example, the input is blocks equals 1 and split equals 2. Since we only have one block and one worker, there's no need to split the worker. The worker can directly build the block in 1 unit of time, so the output is 1. This demonstrates the simplest case, where splitting isn't necessary. In the second example, we have blocks equals 1, 2, and split equals 5. Here, we start with one worker, but since there are two blocks, splitting the worker is necessary. At time 0, the worker splits into two workers, which takes 5 units of time. At time 5, both workers can simultaneously build the two blocks. The block times are 1 and 2, so the overall time to build the blocks is determined by the maximum of these, which is 2. Adding the splitting time of 5 gives a total of 7 units of time. This example shows the trade-off between splitting time and parallelizing the work. In the third example, we have blocks equals 1, 2, 3, and split equals 1. Here, we need to handle 3 blocks but only start with one worker. At time 0, the worker splits into two workers, taking 1 unit of time. At time 1, one of these workers splits again, creating a total of 3 workers, and this also takes 1 unit of time. By time 2, all 3 workers are available and can build the 3 blocks simultaneously. The block times are 1, 2, and 3, so the maximum time taken to build the blocks is 3. Adding the splitting times of 1 and 1 gives a total of 4 units of time. This example highlights the efficiency of splitting when the cost is low and the number of blocks is high. When considering edge cases, there are several important scenarios to keep in mind. If there's only one block, no splitting is necessary, and the output is simply the time required to build that block. If the splitting cost is very high compared to the block times, it might be more efficient to avoid splitting and use fewer workers. Conversely, if the splitting cost is very low, splitting extensively may be the best strategy to parallelize the work as much as possible. For a large number of blocks, managing workers efficiently becomes critical to minimize time. The key idea is to balance the trade-off between splitting workers, which adds time, and parallelizing work, which reduces the time to build blocks. Solving this problem efficiently might involve advanced methods such as greedy algorithms or dynamic programming to prioritize the largest block times and ensure they are handled efficiently. To solve the minimum time to build blocks problem, our goal is to minimize the total time required, balancing the time spent splitting workers with the time needed to build the blocks themselves. One possible approach is the brute force method. The intuition here is to explore all possible ways to assign workers to blocks, considering splitting times at each step. This involves generating all combinations of assignments and recursively calculating the total time for each scenario. However, this approach is computationally expensive, with a time complexity that grows factorially, n, or worse, as the number of blocks increases. This makes it infeasible for large inputs. Another approach we considered is the greedy strategy. Here, the focus is on tackling the largest blocks first, sorting the blocks in descending order, and assigning workers to the largest available block at each step while splitting workers as necessary. While this method might seem effective, it fails to guarantee the minimum total time because it doesn't account for how splitting workers early impacts the cumulative time to handle smaller blocks later. These limitations highlight the need for a more efficient and globally optimal strategy. The optimized approach uses a priority queue, or min-heap, to efficiently minimize the total time. The key insight here is that combining the smallest blocks first reduces the long-term cost of splitting workers. This is similar to the logic used in Huffman coding. The steps are straightforward. First, add all blocks to a min heap. Then, while more than one block remains, repeatedly pop the two smallest blocks from the heap, combine them into a new block while adding the splitting time, and push the combined block back into the heap. The process continues until only one block remains, which represents the total time required. This approach has a time complexity of O(n) log n, thanks to the efficient insertion and deletion operations of the heap, and a space complexity of O(n), which accounts for the heap storage. By always combining the two smallest blocks, this method ensures that the cumulative time cost is minimized, making it both optimal and efficient. The heap-based approach was chosen because it achieves the best balance of efficiency, clarity, and correctness. One of the key observations is that combining smaller blocks earlier minimizes the cumulative time cost of splitting workers. Additionally, the problem structure, which involves minimizing a cumulative cost, naturally aligns with techniques like Huffman coding that use heaps to repeatedly combine the smallest elements. Sorting the blocks alone cannot achieve this dynamic prioritization, which is why the heap structure is critical. In terms of trade-offs, the brute force method was ruled out due to its exponential runtime, and while the greedy approach is faster, it fails to consistently find the optimal solution. By leveraging the heap-based strategy, we solve the problem within O(n) log n time complexity while ensuring the minimum possible time to build all blocks. This makes it the most effective and reliable approach for this problem. This problem revolves around minimizing the total time required to construct all blocks, where each block has a specific build time provided in the blocks array. The challenge arises because workers can split into two, allowing them to work on multiple blocks concurrently, but each split incurs an additional cost of 1 unit of time. The goal is to find the minimum time to complete all block building tasks. To achieve this, we rely on a few key insights. First, larger blocks should be handled with priority because they take longer to build, and pairing smaller blocks earlier helps reduce the overall time. Second, a min-heap data structure is ideal for efficiently accessing and combining the smallest block times, as it allows us to retrieve the two smallest elements in logarithmic time. Finally, managing the cost of splitting workers and balancing it with the building time is crucial for minimizing the total time effectively. To solve the problem, we can break the algorithm into clear steps. First, we handle input validation and initialization. If there is only one block, we simply return its build time since no splitting is needed. For multiple blocks, we create a min-heap from the blocks array, which allows efficient processing of the smallest block times. Next, we simulate the building process. We start with one worker and process the blocks iteratively. If there are fewer workers than blocks, we split workers to match the number of blocks, and each split adds 1 unit of time to the total. Then, we use the available workers to build blocks in parallel, extracting the smallest block times from the heap and recording the maximum time taken in each round. After completing a round of building, the results are pushed back into the heap to represent partially completed blocks that still need further processing. This process is repeated until all blocks are fully built and the heap is empty. Once all blocks are processed, we compute the total minimum time by summing the time spent on splitting workers and the build times. To implement this efficiently, we rely on a few key data structures and operations. The min heap is central to the algorithm, allowing us to store and retrieve block times efficiently. Heap operations like push and pop run in O log n, ensuring the algorithm scales well for larger inputs. Additionally, counters are used to track the number of workers and the blocks completed. The two main operations are splitting workers, which increases the worker count when more workers are needed than are currently available, and building blocks, where we extract the smallest block times from the heap, process them, and push the results back into the heap. Together, these components ensure that the algorithm is both efficient and accurate in minimizing the total build time. Analyzing the algorithm's efficiency, the time complexity is O(n) log n, dominated by the heap operations. Each block is processed n times, with each operation requiring O log n, making the approach suitable for large inputs. The space complexity is O(n), due to the heap storage for block times. Several edge cases must also be considered. For a single block, no splitting is required, and the result is simply the block time. If all blocks are the same size, the algorithm still ensures minimal splitting overhead by processing blocks efficiently in parallel. For large inputs, the heap's efficiency ensures the algorithm remains within computational limits, making it robust enough to handle diverse scenarios. To better understand the algorithm, let's walk through an example with blocks equals 1, 2, 3, 4. We first initialize the min heap as 1, 2, 3, 4. In the first round, we split workers to process all blocks, which incurs a cost of 1. Then, we build blocks in parallel, focusing on the smallest times, so 1, 2, are processed with a maximum time of 2. The results are pushed back into the heap, which now becomes 2, 3, 4. In the second round, we process 2, 3, taking a maximum time of 3, and the heap updates to 3, 4. Finally, in the third round, 3, 4 are processed with a maximum time of 4, leaving 4 in the heap. Summing the time for splitting and building gives us a total of 1 plus open parenthesis 2 plus 3 plus 4 close parenthesis is equal to 10. The result is 10, demonstrating how the algorithm minimizes the total time effectively. This solution minimizes the time required to build all blocks using a greedy approach with a min heap. First, the heap.heapify function is used to convert the input blocks array into a min heap, which allows efficient extraction of the smallest elements. The main idea is to repeatedly combine the two smallest build times, since minimizing the time spent in earlier splits leads to a lower overall construction time. In the while loop, we check if there are more than one block left to process. If so, the two smallest elements are extracted using heap.heappop. These correspond to the two blocks that can be built in parallel after a split operation. The cost of this operation is the split time plus the greater of the two build times, since they can be built in parallel. The combined time for this new task is then pushed back into the heap using heap.heappush. This ensures that the heap remains ordered and the smallest elements can be efficiently accessed in the next iteration. The process continues until only one block remains in the heap. At this point, the value of the last remaining element represents the minimum time required to build all blocks. This algorithm efficiently handles the problem in n log n time due to the heap operations, making it suitable for input sizes up to 10 to the power of 4 blocks. This approach ensures correctness by always prioritizing the smallest build times, which minimizes the cumulative penalty of larger build times during subsequent splits. Here, we're implementing the solution in Java using a priority queue, which will help us simulate the behavior of a min heap. First, we declare and initialize the priority queue to store the build times of the blocks. Then, we populate the heap by iterating through the array of block build times and adding each value to the priority queue. This ensures that the smallest build times are always accessible. Next, we enter a loop that continues as long as there is more than one block in the heap. Within this loop, we remove the two smallest elements from the heap using the poll method, which retrieves and removes the smallest element. These two values represent the two blocks with the shortest build times. We then calculate the new combined task time by adding the split time to the larger of the two values, which ensures we account for the time required to split and build these blocks. The resulting combined time is added back into the heap, effectively reducing the number of tasks. This process continues until only one element remains in the heap. Finally, once the loop has completed, the last remaining element in the priority queue represents the minimum time required to build all the blocks. This value is returned as the result of the function. By leveraging the priority queue and its ability to efficiently manage and retrieve the smallest elements, this approach ensures that we minimize the overall build time while handling the constraints of splitting and combining tasks effectively. To solve this problem, we start with a small input example where the blocks are 1, 2, and the split time is 5. First, we organize the blocks in a min heap structure using Python's heap library, which helps us efficiently get the smallest values. After heapifying, the heap becomes 1, 2. Now, in the main loop, we repeatedly pop the two smallest build times from the heap. Here, we extract 1 and 2. To merge these two blocks into one task, we calculate the new time as the split time plus the larger of these two values. This gives us 5 plus max, 1, 2, equals 5 plus 2 is equal to 7. We then push this new task, 7, back into the heap. At this point, the heap contains only one value, which is 7. Thus, the minimum time to build all blocks is the remaining value in the heap, which is 7. Now, let's consider a medium input example where the blocks are 1, 2, 3, and the split time is 3. Again, we start by heapifying the blocks, which results in the heap 1, 2, 3. In the first iteration, we pop the two smallest build times, 1 and 2. We merge these by adding the split time and the larger of the two values, resulting in 3 plus max, 1, 2, equals 3 plus 2 is equal to 5. We then push this new task back into the heap, so the heap becomes 3, 5. In the second iteration, we pop the two smallest values again, which are now 3 and 5. We merge these into a new task, computing the time as 3 plus max, 3, 5, equals 3 plus 5 is equal to 8. This new task is pushed back into the heap, leaving us with 8. With only one block remaining, the minimum time to build all blocks is 8. For a larger input example, we have blocks 1, 2, 3, 4, and a split time of 4. Once heapified, the blocks become 1, 2, 3, 4. In the first iteration, we pop the two smallest values, 1 and 2. Merging them gives a new task with a time of 4 plus max, 1, 2, equals 4 plus 2 is equal to 6. This value is pushed back into the heap, resulting in 3, 4, 6. In the second iteration, we pop the smallest values again, which are now 3 and 4. We merge these into a new task with a time of 4 plus max, 3, 4, equals 4 plus 4 is equal to 8. This is pushed back into the heap, leaving us with 6, 8. In the third iteration, we pop the two smallest build times, which are 6 and 8. Merging these gives a new task with a time of 4 plus max, 6, 8, equals 4 plus 8 is equal to 12. This value is pushed back into the heap, leaving only one block. The final step is to return the last remaining value in the heap, which is 12. This is the minimum time required to build all the blocks for this input. To determine the time complexity of this problem, we begin by analyzing the operations involved when using a min-heap. The first step is to convert the input list of blocks into a min-heap using the heap.heapify function. This initial heapify operation has a time complexity of O, n, where n is the number of blocks in the input array. Once the heap is created, the main work happens inside a while loop, which continues until there is only one block left in the heap. In each iteration of the loop, the two smallest elements are removed using heap.heappop. Since removing the smallest element from a heap of size k takes O log k, and we perform this operation twice per iteration, the total cost for removing the two smallest elements is O, 2 asterisk log k, or simply O log k. Then, after computing the new combined block, we push it back into the heap using heap.heappush, which also takes O log k. Altogether, the total cost per iteration of the loop is O log k. Now, let's consider the number of iterations in the while loop. Since we reduce the heap size by 1 in each iteration, the loop runs approximately n1 times. Combining this with the per iteration cost of O log k, the total cost of the while loop becomes O n1 asterisk log n, which simplifies to O n asterisk log n. To calculate the overall time complexity, we add the cost of the initial heapify operation, O n, to the cost of the while loop, O n asterisk log n. Since O n asterisk log n dominates O n as n grows larger, the final time complexity of the algorithm is O n asterisk log n. This efficiency is a result of leveraging the properties of the min-heap to minimize the costs at each step. Let's now analyze the space complexity of the algorithm. The primary space usage comes from the heap itself, which stores the blocks. Since the heap contains all the blocks initially and reduces in size as the algorithm proceeds, its maximum space usage is proportional to the number of blocks, or O, n. Beyond the heap, the algorithm does not use any additional data structures or make recursive calls that would require extra memory. The intermediate variables, such as first, second, and new underscore time, are simple integers and therefore require only O1 space. Combining these considerations, the total space complexity of the algorithm is O, n, dominated entirely by the space needed for the heap. When comparing approaches, it's clear how efficient the heap-based method is. A brute force approach to solving this problem would involve generating all possible ways to group the blocks and recursively computing the minimum time for each configuration. This results in an exponential time complexity, specifically O2 to the power of n, in the worst case, due to the sheer number of combinations that need to be explored. In contrast, the heap-based approach is far more efficient, with a time complexity of n*log n. This is achieved by always merging the two smallest blocks first, which minimizes the intermediate costs at each step. The efficiency of the heap operations heap pop and heap push, both of which run in log k, ensures that the algorithm can handle the constraints typical in this problem, such as n being as large as 10 to the power of 4. Finally, let's examine the best, average, and worst-case scenarios. Interestingly, the runtime remains consistent across all cases. In the best case, where all blocks have the same build time, the algorithm still performs the same sequence of heap operations, leading to a time complexity of n*log n. Similarly, in the worst case, where the blocks have highly varied build times, the algorithm's runtime does not change because the heap operations and their costs are independent of the input distribution. Consequently, the average case is also n*log n, as the heap operations dominate regardless of the input. In summary, the greedy heap-based approach provides optimal performance with a time complexity of n*log n and a space complexity of n, making it a highly effective solution for this problem. One of the most common mistakes in this problem is misunderstanding the splitting mechanism. Some assume that each worker can only split once, but the problem actually allows for multiple splits as needed. This misunderstanding often leads to suboptimal solutions or even incorrect implementations. To address this, it's important to carefully read the problem constraints and ensure your logic supports multiple splits as required. Another mistake is attempting to solve the problem in a greedy manner without using a priority queue. For example, manually selecting the two smallest blocks repeatedly from the list is inefficient and can lead to poor runtimes. Instead, using a min-heap or priority queue allows you to fetch the smallest block sufficiently in log n time. Lastly, developers sometimes overlook edge cases, such as when there's only one block or when many blocks are already the same size. Ignoring these can result in runtime errors or incorrect outputs. To avoid this, you should add specific checks for these scenarios in your implementation and test with minimal input sizes to ensure correctness. Another common pitfall is incorrectly calculating the total time. This happens when developers sum up times prematurely or fail to account for the sequential dependencies created by merging blocks. Remember, merging blocks is a cumulative process, and the order of operations directly affects the total time. To fix this, it's crucial to understand the dependencies and ensure your calculations reflect the merging sequence. Additionally, some developers overcomplicate their logic by unnecessarily using advanced data structures or techniques. While it's tempting to try complex solutions, this often leads to bugs and harder to maintain code. Instead, focus on sticking to the simplest approach that meets the problem requirements, such as using a priority queue for greedy merging. Simplicity in design not only reduces implementation complexity but also improves the reliability of your solution. From an interview perspective, this problem exemplifies a key pattern often seen in coding challenges, the merge cost or Huffman coding style problem. These problems typically involve minimizing a cost function by repeatedly combining elements in a certain order, often leveraging a priority queue to achieve efficiency. The optimal approach here is to use a min-heap to ensure that the smallest blocks are merged first, minimizing the overall time. This insight is fundamental to producing an efficient solution. It's also important to explain trade-offs during an interview. For instance, a brute force approach that tries all combinations of merges is theoretically correct but impractical due to its exponential time complexity, n. On the other hand, the heap-based greedy method reduces this to n log n, making it far more efficient. Clear communication is key. Be prepared to articulate how your solution minimizes time, as well as how you handle edge cases. This demonstrates both problem-solving ability and attention to detail, which are essential in an interview setting. There are several related problems that share similarities with this one. For example, LeetCode 1046, last stoneweight, uses a priority queue in a similar way to manage and minimize merging operations, making it a good practice problem. LeetCode 253, Meeting Rooms 2, is another example that leverages greedy algorithms with a priority queue, but in the context of optimizing resource allocation. Additionally, LeetCode 973, K closest points to origin, provides insight into using heaps efficiently for proximity-based selections. Finally, LeetCode 502, IPO, is a greedy problem that also uses priority queues, but in a scenario where the goal is to maximize a cost-based solution. These problems help reinforce the importance of using heaps and greedy techniques effectively, and practicing them can strengthen your ability to solve similar challenges. When considering alternative approaches, brute force is the most straightforward method. It involves trying all possible orderings of merges and calculating the total time for each. While this guarantees correctness, it's computationally infeasible for large inputs due to factorial time complexity, O(n). The trade-off here is simplicity in implementation versus scalability. Another option is dynamic programming, which involves maintaining a DP table to calculate the minimum time for different subsets of blocks. While correct, this approach is more complex to implement and requires significantly more space. It's better suited for smaller inputs but is often outperformed by the heap-based greedy approach. The most efficient and scalable solution is the greedy method using a min-heap. By iteratively merging the two smallest blocks, this approach ensures minimal additional time at each step, achieving an overall time complexity of O(n) log n. The trade-off is that this method requires familiarity with heaps and priority queues, but it's the most practical for real-world scenarios and competitive programming. Great job! We've reviewed the solution to LeetCode problem number 1199, minimum time to build blocks. The key takeaway here is the power of heaps in optimizing scheduling problems. Thank you for watching, and be sure to like and subscribe for more coding tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!